Today we're going to figure out how to do the spherical transformation from Cartesian coordinates. So first thing is we should probably draw our coordinate axes, the Cartesian, if we're going to be translating from a Cartesian coordinate axis into a spherical one like we have over here. The Z, the X is coming out of the page, and then the Y. Okay, so let's call some vector. We'll say that this denotes our position. So it's some X, Y, and Z. We'll say it's like out here. And just to recall what that means is we've moved some amount in X, some amount in Y, and some amount in Z, and that has gotten us up here. Let's figure out how we can rename this, not as X, Y, and Z, but what X, Y, and Z equal, what X equals, what Y equals, and what Z equals in spherical coordinates. Let's go ahead and project this down into the XY plane. I'll do it in red. So we've projected it down into the XY plane. How you can think about that too is, imagine if we had like a flashlight up here and we were shining it on like a stick. This is the shadow of the stick. The shadow of the stick is like a projection on the XY plane if we're shining from above. Anyway, now that we have the projection over here, let's look at it in terms of X and Y. Here we have a portion, and here we have a portion. I'll go ahead and write it as R, which is the maximum length, multiplied by X to Y is phi. So this piece is R adjacent, which is cosine, and all that the cosine of phi is doing is scaling the R. R would be out here somewhere, and the cosine makes it smaller, because recall that all trigonometric functions really do is they're like percentages. So it's saying, like, I want this percent of R as my X projection, and I want this percentage of R as my Y projection once I project this into the XY plane. R sine, because now we're using the opposite angle. And we're not going to pick up anything from Z here. So let's go ahead and now project this into the ZY. Do it in green. Recall this angle over here, we call phi. Well, I suppose it would be longer, but I guess it doesn't really matter. Okay, so over here we have some portion, and over here we have some portion. The adjacent side, the cosine, is basically just in the Z direction. So we can go ahead and write that in, cosine of theta, because we're using a different angle now. And notice this piece right over here can be in the Y, or it can be in the X. It's symmetric around Z. So we need to put this piece, which is the sine, because it's this side over here, and this is the angle. So sine theta sine theta. Okay, and the idea behind this once again is recall this R, distance in the I direction, plus some distance y, in the j hat direction plus some distance z. I don't know what I was thinking right there, in the k direction. And what we're effectively going to do is put this inside here, and put this inside here. Alright. So let's go ahead and plug those new representations of x, y, and z into the position vector r. Plug it in, we have r is equal to r cosine of phi sine theta in the I direction. I, j, k is like x, y, z. Many physics books switch between the two, or you'll be using books by different authors in your physics career, so it's a good idea to just get used to I, j, k as well. Plus r sine phi sine theta j direction plus r cosine theta in the k direction. We want the unit vectors from this information. What are those? R, how radially far you are. Theta, we have phi. In order to get these, we're going to have to do dr by little r. Then we're going to have to do dr d theta, and similarly dr d phi. And we're going to have to do this for each of the elements. So dr capital by dr little for this element, and this element. Similarly for this one and for this one. And actually, it might be better if I rewrite them in their true form. It might be more enlightening. So we have dr by dr, right? But we said it's a unit vector, so what does that mean? We have to divide by the magnitude of dr by dr. These expressions for theta hat and phi hat. We have to divide by the magnitude in order to make sure that these values are equal to 1, because we're using them as the basis for telling somebody how far something is away from us in terms of these unit vectors. I'll rewrite it for convenience as well. So recall big R, R cos phi sine theta, right, in the I direction, plus R cos, sine phi sine theta in the j direction, plus R cos theta in the k direction. Now we have to take this with respect to r, so it's going to be cosine phi sine theta, because these are constants. We're doing it to this piece right over here in the I direction, plus this one still with respect to r, so sine phi sine theta in the j direction, plus cosine theta in the k direction. Theta hat is going to be by derivative. We look at this one and we take the derivative with respect to theta. The derivative of this is going to be cosine of theta. So this is going to be r, which is a constant. The phi term, which is a constant. The derivative of the theta term. The I direction. Plus constants. We'll go ahead and just put those in there. The derivative of the theta term is cosine again. Plus, over here we're going to get a minus r sine of theta. I have to put in directions. So now, let's look at this one over here and take the derivative with respect to phi. So we're going to get a minus sine of phi times the constants. Plus, let's go ahead and take a look at this one. We're going to get a cosine of phi, so r sine theta cosine phi. And let's go ahead and look at the last one. It's all constants, and the derivative of a constant is 0 in the k direction. So congratulations, we have proven what the new unit vectors are for our spherical transformation from Cartesian coordinates. And now that we've found what the unit vectors are in spherical coordinates, let's go ahead and find what our volume elements, area elements are, and line elements are. D tau is going to be our little change in volume. And d dr row first. So d dr, d by d, column, d dr, column. And then we'll do the d phi, d phi, and we'll do d by d theta last as the last column. We'll go ahead and put them in as rows now. So x is the first row, y is the second row, and you guessed it, z is the third row. Recall, we stated that x was r cosine of phi sine theta, y was r sine phi sine theta, and z was r cosine of theta. So it's our job to go ahead and do all of these. We'll go ahead and do the row method. I'll write 2 extra columns actually. So I'll write one of these and one of these over here. So okay, and we'll use that diagonal downs minus the diagonal ups method. So I'll do purple. We'll grab this. Will be our first diagonal down. This will be our second diagonal down. This will be our third diagonal down. We'll take this one. Take this one right over here. And this one should do just fine for us. And when we do the purples, minus the oranges, the result of this is going to be r squared sine of theta dr, d phi, d theta. And this is our volume element. Originally, if you've been watching all the videos, I said dl was going to be dl, an infinitesimal line element in this spherical coordinate system, was going to be dr, because the first coefficient was 1, plus r d theta plus r sine theta, right over here. We want to go ahead and take a look at our area elements, dA. When r is constant, we pick up this one, and we pick up this one. And we say r squared, where this r is the constant, so it would be like some value, r squared sine theta d theta d phi. We'll just put r const here. So here, when we have theta constant, just to be clear, r direction, theta direction, and phi direction. But so dA, when phi is constant, so don't worry about this one, we have r dr, and also d theta. In the phi direction, because phi is constant. This one is in the r direction, because r is constant. And finally, when theta is constant, we have this one and this one. So r sine theta dr d phi in the theta direction. And those are our line, area, and volume elements in spherical coordinate systems transformed from Cartesian coordinate system.